Okay, so we are going to be looking at trigonometric substitution. First, let's begin with our identities, right? Tan squared plus 1 equals secant squared. Secant squared minus 1 equals tan squared. And 1 minus sine squared equals cosine squared. This is what we are going to do. This is what we're going to use when we do these trigonometric substitution problems. And what it's going to let us do is it's going to let us take things that look like something times x squared plus something and turn that into a much cleaner form, especially when it's like under a square root or something, that allow us to use a trigonometric substitution that with along these identities give us something simpler that we can actually take the square root of, okay? So if we have bx squared plus a squared, right? We can rewrite this by dividing by all the sides of our triangle. Right? This is our triangle, right? If we have bx squared plus a squared, that's the hypotenuse for the triangle that has bx over here and a over here, right? And if that's the hypotenuse, then our tangent would be the two nice things, bx opposite over adjacent, right? Or if you want to divide everything by a, we get bx over a, 1, and this square root right here, right? And so what we can do is we can divide the a out from here and get this form right here, and then stick a tangent here. That tangent squared will turn in with the plus 1 turns into a secant squared, and we can take the square root of that secant square and go from there with the integral, right? It's a really, really nice algebra trick that allows us to do a kind of high-level U substitution thing in order to get trig functions that we can take integrals of, and then use this. This is going to be the key right here, our reference triangle. This reference triangle is going to let us go from x's to thetas, and then from thetas back to x's when we get the antiderivative. Okay. And since these are SOHCAHTOA triangles that work for kind of all numbers that you can have on sides of the triangle, so we can use these for kind of any size x that we might want to have. Right? It also works for here and here, like negatives, if you want to have around the unit circle, right? You can still have like negative x's and negative y's. So we're not particularly restricted with what x's we can use here. Okay. Our second one comes from this triangle right here, right? Cosine is opposite over hypotenuse, and secant is hypotenuse over opposite. And when you use the Pythagorean theorem to solve this, you get this squared minus this squared equals this squared, so we can square root it with this. And it turns out that this form right here, when you divide by a, gives you this form right here. And this form is perfect for our secant squared minus 1 identity to become a tan squared, right? So this form of the x squared thing minus something goes with secant squared, right? The x squared thing plus something goes with tangent. The x squared thing minus something goes with secant. Our last triangle, it looks just like this one, except for look, instead of having the bx on the hypotenuse and the a on the adjacent, we have the a on the hypotenuse and the bx on the opposite, right? So when we do this, there's our theta, opposite over hypotenuse is sine. So sine theta equals bx over a, right? And we're going to use this form again by dividing out the a. So when we have 1 minus bx over a squared, we put a sign in there. we get 1 minus sine squared, which is just cosine squared, which we can take the square root of, and it works nicely. Okay. Put this on the next page. Okay. So it's hard to see how this works until you do a problem, right? And then you'll kind of get a feel for how it works, because it's hard to think about how angles and trig functions are tied to x's, but it's really just the SOHCAHTOA ratios, right? And the trig identities, right? Okay. Now let's look at some identities that are really helpful in doing these types of problems. The first one is cosine squared equals 1/2 plus 1/2 cosine 2x, right? The second one is sine 2x equals 2 sine x cosine x, right? And this is really useful in doing this integral right here. The integral of cosine squared, we rewrite it as this. You don't have to rewrite it like this. You can integrate it using integration by parts, but this is easier. When you integrate 1/2 and you get x. You integrate 1/2 cosine 2x, you get 1/4 sine 2x, right? But sine 2x can be rewritten as sine x cosine x, or 2 sine x cosine x, and the 2 and the 1/4 cancel out, right? This is an integral that we'll see when we do the trig substitution. Another one we see is secant x. Secant x is kind of a crazy integral. Someone figured out that if you multiply by 1 in the form of secant x plus tan x over secant x plus tan x and multiply by secant x in the top, that the top thing is actually the derivative of the bottom thing, right? Secant squared is the derivative of tan, and secant x tan x is the derivative of secant. Right? So this right here, secant x is the derivative of the tan, and this right here is the derivative of the secant. So you can think of this as being 1 over secant x plus tan x times its derivative, which is perfect for a substitution. And when you do the substitution, because this is the derivative right here, right? Because that's the derivative, when you solve for dx, the thing up here is going to cancel out with the thing under the dw when you solve for dx equals, and you'll get a really nice clean integral of just 1 over w, which becomes ln w, which becomes ln secant plus tan, right? It's kind of crazy. Feel free to look over that one. The one I didn't even do because it's just kind of really lengthy is secant cubed. It involves using integration by parts, right? And lots of heartache apparently. And you get this integral right here when you do that, right? If you want to, you can look it up on the internet, it's there, but I'm just going to tell you that's the integral. Okay? So let's see why I showed you these by looking at an example. The first one is x squared minus 1. So when we have something x squared minus something, that's this one right here, right? That's your secant, right? I guess I should go up to here. Something squared minus 1, right? That's like something x squared minus something. When you have that form where you put in, say, what trig function am I going to do to get, you know, x squared minus 1 is what you want to look at, and that's secant. Right? So secant is what we're going to do. And let's see. A is 1, B is 1, so we don't have to do any simplifications here. We just do secant x, secant theta equals x, and we do our dx d theta, right? And then we can substitute in for secant, substitute in for dx, right? Then we use that trig identity, right? The secant squared minus 1 equals tangent squared, and all of a sudden, our square root goes away because the tangent squared equals tangent, right? The tangent squared equals tangent right here. Right? Tangent is going to be in our triangle, right? That's going to be the hypotenuse thing. So you don't have to worry about it being negative. It's going to be tangent side hypotenuse. It's second positive right there. All right, so that's tangent squared. That's secant tangent. Well, you can try doing substitutions on this, but none of them work. So you want to take tangent squared that we got now by taking the first thing we need to do is get rid of the square root. Then when you get rid of the square root, you can say try different stuff, but the thing that's going to end up working out is calling tangent secant squared minus 1. So we went from secant squared minus 1 to tangent squared to get rid of the square root. Then we go from tangent squared back to secant squared minus 1 to get secant cubed minus secant. Secant cubed, this thing right here. Secant, this thing right here. So we take our antiderivatives, simplify it, and we get this expression right here. Right? So what I want you to focus on is this step right here, right? The substitution in and substituting back in for x using our triangle. Okay? So this is the antiderivative that we got. We would like to rewrite this as a antiderivative in terms of x, right? Because this, right, this is what our antiderivative is as a function of theta, but theta is a function of x, right? X equals secant theta, theta equals secant inverse s, but let's not say that. Let's just look at our triangle, use the ratio for it. If x is secant theta, secant is hypotenuse over adjacent. So hypotenuse over adjacent is x. So put x on the hypotenuse and 1 on the adjacent. And then the opposite is going to be x squared minus 1. Okay. So secant is x over 1. Tangent is opposite over adjacent. So tangent is x squared minus 1 over 1. So secant, hypotenuse over adjacent, x, tangent, opposite over adjacent, square root of x squared minus 1. So we replace our secants with x's and our tangents with square root of x squared minus 1. That's the key step right there. All right, example 2. So here's our something x squared plus something. Well, something x squared plus something is the one that matches with tangent squared plus something, right? Plus 1, tangent squared plus 1. The squared thing plus, the squared thing minus, 1 minus the square thing, right? That's kind of your form. Well, what we have here is the x squared stuff plus something, so that's going to be tangent. First, we need to have a 1 here. So we divide out the square root of 5 to get a 1. Then we need to rewrite this as just something squared. Well, the something squared is square root of 2 over 5x. Now we're ready to call this thing in here a tangent. So we call this thing in here a tangent. Then we solve for x and take the derivative with respect to theta of x, right? So this is our substitution to get us the tangent squared, but to get the d theta, we have to solve for x and take dx d theta, right? That's the way we're going to get our d theta stuff. We did that up with secant again. Let me show you. I probably glossed over it too easily. X equals secant. Then we take the dx d theta derivative to get our dx that we can substitute in to get our d theta stuff. So here we solve and we get dx equals square root of 5 over 2 secant squared theta because the derivative of tangent is secant squared. Okay. Now we can do all of our substitutions. Right? First we go to here. Right? Go from here. We're going to substitute in for that and call it tangent. And then we're going to substitute in for that and call it square root of 5 over 2 secant squared d theta. Then we're going to simplify. Square root of 5, square root of 5, cancel out, and that leaves us with 1 over the square root of 2. Let's pull that out front. Tangent squared plus 1 becomes secant squared. Well, we can take the square root of that, right? We can take the square root of secant squared. Right? That's really nice. Right? And that just becomes secant. Secant squared stays secant squared. Secant squared over secant cancels out and just leaves us with this. This was one of our ugly integrals. This one right here, the green one. And we do our ugly integral and we get this. But now we would like to resubstitute our theta integral back to get our x integral, because our integral was an x to start out with. And this is just our u substitution. So we're going to resub, right? We use a secant. So secant, use tangent. So tangent is opposite over hypotenuse, right? So tangent was the opposite over the hypotenuse, and it's really nice just to make the thing that it's over 1 in your triangle, right? And so it's just basically tangent will just be the opposite one. Then the Pythagorean theorem gives us that this is the hypotenuse, right? Secant is hypotenuse over adjacent. So anywhere there's a tangent, we're going to use this one. Anywhere there's a secant, we're going to use this one. There's a secant there. There's a tangent there. And now we have our x antiderivative. And it's ugly, but it works, right? It works real nicely. Okay. One more example. If you're looking for the area of an ellipse, right? An ellipse, we can solve for it. Oh, right here. Try that again. All right. So we have 3x Well, if we solve for y, we get y equals square root of 4 minus 3x squared. All right. This minor axis on the x-axis goes from negative 1.115. Well, that's just if we solve for 4x minus 3x squared equals 0, what we get is 2 over the square root of 3. Or negative 2 over the square root of 3. So those are the x bounds of this axis. So what we're going to find this area under the blue, which would be from negative 2 over the square root of 3 to positive 2 over the square root of 3 of our square root function, which is just the top half of our ellipse. Okay. All right. What we have here is something minus something with x squared. We want it to be 1 minus, right? So you always want to get a 1 as the other number. So we divide out the 4. We get this. Then this is 1 minus something squared. Well, that's going to be our sine triangle that we're going to use. Right? So sine is what you get when you get 1 minus something squared. Well, that something that we're squaring is, let me get to it, square root of 3x over 2, right? And notice that this is just the reciprocal of our x-bound things, because we want 1 minus that to be 0. When x is 0 are where our 2 bounds for the minor axis there on the x-axis is. So it's always going to be kind of the reciprocal of the coefficient when you have it in the square thing, right? Let's just take note of that. that the limits of integration are the reciprocals of the x coefficient right here, right? Okay, so this is the thing we're going to turn into sine. So sine is opposite over hypotenuse. So this is going to be our opposite. 1 will be our hypotenuse, and the adjacent is going to be 1 minus this, right? This square thing is going to be our adjacent side in our triangle. So first we set this equal to sine, but we also solve for x. Why do we solve for x? Because we're not just going to substitute in for sine, we're also going to substitute in for dx. And solving for x allows us to take dx d theta and get this cosine thing, right? We're going to note one more thing. If this is true, then this will also be true, okay? If this is true, this will also be true, okay? Because this ratio, right, in order for it to work in the 1 minus x squared stuff, right, this ratio for sine over 1, you know, it's going to work, excuse me, right? It's going to work if for any of the positive or negative numbers that we're going to be kind of worried about under our square root here, because you're only allowed to, when you do 1 minus x squared, right? Since we're going to get positive numbers in our square root, x has to be such that we're only going to be looking at the numbers on our little axis here. And those numbers on our little axis here are going to be the numbers that keep this ratio right here between -1 and 1. So we can use our sine inverse function right here. Okay. Why do I point that out? Because we're going to see that in the integral when we do it. Okay. Okay, so first I substitute in for the x right here, sine, and I get 1 minus sine squared, but 1 minus sine squared is cosine squared, and the square root of cosine squared is just cosine. Right? So I can get rid of my square root by using that. dx d theta is this, which means I can substitute in dx with this one right here. Square root of cosine squared times cosine. Square root of cosine squared is cosine. Cosine times cosine is cosine squared. Cosine squared was one of my ugly integrals that we see, the tricky ones, I guess. It's the first one right here that uses the double angle stuff. So by using the double angles in that integral, I get this right here. Right? I factored out the 4 over the square root of 3. That comes from this one here. And the 2 that I took out to get the 1, to get a 1 here, we took out the 2 right there. Then we get the 2 over the square root of 3, so we get 4 over the square root of 3 times this. Okay. Now we want to do a substitution back for x. Our first substitution is theta. When we do our theta substitution, we get this one right here. Okay. Now, the other ones that we do are sine and cosine. Remember, sine is opposite over hypotenuse, and since sine is this, we call this the opposite and 1 the hypotenuse, which makes cosine this thing right here, right? This thing right here is cosine. So where I have a sine, I just put what we set sine equal to. Square root of 3 over x. Square root of 3 over 2. Oops, I had it backwards. Let me fix that. It should be square root of 3 over 2. Not 2 over the square root of 3. All right. Okay. Yeah, good. So this is our sine, this is our cosine, but a really cool thing happens when we plug in our limits of integration. Remember how I said that these numbers, when you plug them in x squared, cancel out the 3/4 and give you 1, right? That's what puts you at 0 on your axes, your x equals 0 on your axes. Your two limits of integration are the things that zero out the cosine term, right? Right? Zero out the cosine term. So when you zero out the cosine term at both the top and the bottom and it multiplies by this other stuff, it just zeroes out this whole thing, right? It zeroes out this whole thing. Oh wait, I see what I did. I don't know why I got that. It should be 2 over the square root of 3, and those should just cancel out. It's weird. Okay. Well, anyway, you get 0 there, right? So you get 0 right there, and 4 over the square root of 3. And that should be a 2. Nope, that was 2 over square root of 3. Yep, that's right, that's right. That's good. So that just cancels out and leaves you 0. Okay, good. That's not the one I'm interested in. That's why I kind of didn't care about the numbers. I still wanted to get them right, but that's not what's important. What's important is this term right here, because here's where you plug in these numbers. But again, it's rigged up so that they're kind of reciprocal numbers. So when you plug in the top one, it's going to cancel out the square root of 3 over 2 and give you 1. When you plug in the bottom one, it's going to cancel it out and give you -1. So every time you do this, no matter what the ellipse, it's going to give you these reciprocals to the coefficient of x that are going to give you 1 and -1 for your sine inverse. Sine inverse of 1 is pi over 2. Sine inverse of -1 is -pi over 2. Pi over 2 minus -pi over 2 is just pi, right? So 2 over the square root of 3 pi is half the area, right? So the total area is 4 over the square root of 3 pi. Right? Let me show you where the 2 comes from. The 2 comes from the 4, right? And the square root of 3 comes from the 3, right? If you were to write this in remember you had this form. Right. Let's see. X and the Y. No, I like the other thing. Let me just go back to it. Right. If you wanted to find a general formula, you could put like an a squared, b squared, and r squared and do the same integral, and you would come up with a nice general formula for ellipses. I'll just tell you that. And you do this thing, and you're going to get the pi and pi halves and pi halves to get pi, and there's going to be a's, b's, and r's somehow in here, and you multiply it by 2 to get the area of an ellipse. Right? Fun fact, you can do it using polar coordinates. I'm not going to require that. I just want you to see sort of the, how to do the integrals. The main thing I want you to see is using the triangle to do the forward substitution. So going from x's to thetas, and then using the triangle to do the inverse substitution, going from thetas to x's. That's the real skill that I'm going to ask you to do on the homework, right? I'm not going to ask you to solve the integral. I'm just going to ask you to do the substitution here, right? I'm not going to ask you to solve the integral. I'm just going to ask you to do the substitution here, right? Okay. Same thing here. I'm not going to ask you to do the substitute. Oh, sorry. This is the substitution for this one. This is the substitution for this one. This is the substitution for this one, which means you have to complete the square in order to do that one. This is the substitution for this one, which means you have to complete the square in order to do that one. And all I want to do is see the substitution. Okay? That's all I want to do is see the substitution. Right? Oh, this one's kind of fun, isn't it? Yeah, I'll leave that one to you. Don't worry. It'll be fine. Right? You can see what we get when we do this one. This one takes a little bit of work. Right? Here, I say, well, suppose that, don't worry about it. We get this integral, this antiderivative. Use this original substitution and re-substitute back in to get the x expression. So this is before we integrate what we do. This is after we integrate. What do we do to get our antiderivative in terms of x? And so I ask you to do that with this trig substitution, this trig substitution, and this trig substitution with these expressions. Okay. It's not easy, but it's worth kind of going through and just practicing to get a feel for these. And I'm going to be happy to help you, but that's all I want to say about these. Okay. Yeah, the substitutes back. What I would always recommend is go to your triangle, right? Go to your reference triangle with hypotenuse over adjacent for secant and when you have something like this, make this your hypotenuse and make your adjacent 1, right? That's always going to be nicer. With opposite over hypotenuse for sine and with opposite over adjacent for tan, okay? This one's actually going to be probably the toughest one right here, number 4 is my guess. But you can do it. All right, that's all I want to do for the video. That is the last video we have for the class. And any other internet stuff you want to use to help you with trig substitution, feel free to use that.